The mission records show that Starship Flight 11, executed on October 18, 2025 from Boca Chica, Texas, achieved an apparent state of operational perfection, completing an entire flight profile from launch to controlled splashdown with no explosions, no telemetry loss, and no unexpected collapse of the system. This was not a test that ended in failure, but a mission where the physics seemed, for the first time, to agree to cooperate. Yet, in aerospace, success is not a final destination, it is only a conditional state granted until the next variable appears. The core paradox of the mission is that Starship worked so flawlessly that it revealed new, previously hidden ways in which the system could fail, forcing engineers to abandon the illusion of absolute triumph. The Starship architecture is defined by a network of mechanical tolerances pushed to their absolute limit, beginning with the propulsion stage, super heavy. During the ascent phase, 33 Raptor engines ignited in sequence, generating 16.9 million newtons of thrust, an unprecedented figure. For the first time, not a single engine cut out prematurely, with every measured vibration frequency matching the initial simulation data. The chamber pressure in each engine runs at 330 bar, which is higher than any other operational engine in history, demanding that the twin turbopumps rotate at 36,000 RPM to feed cryogenic methane and oxygen through dual preburners. Post-flight analysis confirmed that all chamber pressures remained within a tight +2% of nominal for the entire ascent, demonstrating stacked tolerances where a single microscopic crack in an impeller could otherwise amplify into structural failure in milliseconds. The institutional mindset behind this flight was defined by a ruthless pragmatism, prioritizing rapid data acquisition over the conventional slow validation of virtual models. The flight plan was an unprecedented hour-long operation designed to close every single operational loop: launch, orbital insertion, payload deployment, deorbit burn, and splashdown, so that verifiable data could replace assumption. The engineering team deliberately created a state of controlled failure before the launch, removing tiles from the heat shield to create weakness and forcing the structure to reveal whether it could survive its own wounds. This philosophy calculates the cost of truth in square centimeters of missing ceramic, operating on the principle that the loss of hardware is cheaper than the continuation of ignorance. Re-entry subjected the vehicle to extreme environmental constraints, demanding that the thermal protection system, TPS, survive the friction of hypersonic flight. Earlier missions had resulted in tile loss, allowing plasma to eat into the hull, but Flight 11 saw 96.7% of its tiles survive the atmospheric interface. The small number of failures occurred mostly near vent interfaces, which are still prone to acoustic vibration. During this phase, temperatures on the windward surface reached 1,240 C, which remained within the expected margin for the Starship's silicate composite material. However, engineers were keenly aware that the maximum survivable temperature of the composite adhesive was only 1,270 C. That difference of 30 C defined the total thermal operating margin, a window barely wider than the potential error in a single calculation. Internal to the Super Heavy booster, the system executed a critical maneuver that relied on a precise, time-sensitive systemic change. The booster performed a partial return profile, culminating in a 5-engine landing burn into the Gulf of Mexico. This required a new engine clustering algorithm to manage the 5-engine throttling in real time and adjust thrust symmetry for control. Engineers had previously observed differential gimbal lag-inducing roll in earlier tests, necessitating the modification of the hydraulic response delay from 220 minutes down to 175 minutes for this flight. The modification worked, but only narrowly. At T+398 seconds, yaw drift reached 1.2, falling just 0.3 short of the 1.5 threshold that would have triggered an automatic abort sequence. The quiet authority of truth dictates that when a system operates this close to its limits, every parameter is perfect only because every variable is balanced directly on the cusp of failure. NASA analysts initially framed the outcome as flawless, but the quiet understanding among aerospace engineers was that the system had only achieved a temporary equilibrium. When a system this complex stops failing outright, it begins to hide smaller, more dangerous errors beneath the mantle of success. For a precise duration of 0.6 seconds, recorded later in the data, the objective judgment of physics reminded the entire engineering team that complete control is always a conditional, provisional state. The consequences of this conditional control are now transferred to the future vector of the entire program, including the Artemis 3rd lunar landing mission planned for 2027. The post-flight analysis confirmed razor-thin safety margins, the 30C heat shield adhesive margin, the 0.6-second engine pressurization lag, and the 1.5mm structural resonance tolerance. These statistical near failures now define the new operational boundary between mastery and collapse. The reaction of policy is the critical risk inversion. Every flawless test transfers responsibility from the realm of probability to the certainty of policy, a framework that has no margin for 0.6-second errors. The system's survival hinged on the specific material science of its hull, built of 301 series stainless steel. This is a structure where the tank walls are continuous, acting simultaneously as the frame, skin, and primary load path. Unlike common aerospace materials such as aluminum or carbon composites, stainless steel is a comparatively slow conductor of heat, possessing high emissivity. During the peak heating phase, which saw the outer surface reach estimated temperatures between 100C and 1300C, the internal tank walls successfully remained below 200C. This differential in temperature was the exact margin that enabled the system's survival. The primary intellectual error lay in the initial institutional assumption regarding the nature of damage. Engineers had assumed that removing a few tiles would result in a linear increase in heat load confined to small localized regions behind the breach. Instead, the absence of those tiles proved to be a global alteration to the vehicle's aerodynamic shape, causing a reconfiguration of the shock structure across the entire belly. The small hole acted as an amplifier, multiplying the total energy deposition by introducing previously unmodeled coupling factors. The assumption of locality was proven to be the hidden error, forcing the post-flight realization that the design had survived, even though the analysis methods used to predict its failure were fundamentally incomplete. The aerothermal physics of the deliberate breach transformed the heat shield from a protective mosaic into an array of discontinuities. Flight 11 entered the atmosphere with at least 9 tiles missing near the forward flaps, a condition intended to push the material beyond specification. Re-entry at Mach 25 altered the local shock pattern due to the minor geometry change. Subsequent video analysis revealed that the plasma was not merely flowing over the breach, but jetting inward, creating localized vortex heating that pushed the exposed metal skin above 900C, directly approaching the yield limit of the stainless alloy. The most subtle systemic risk emerged during the orbital phase, hours after the main ascent burn. At T+51 minutes during the reignition sequence, telemetry showed a transient oxidizer flow imbalance in one Raptor engine, a subtle deviation that lasted exactly 0.6 seconds. This pressure drop of 5 bar was traced back to condensation inside a vent valve within the autogenous pressurization system, which feeds gasified propellant from the engines back into the tanks. The condensation momentarily reduced flow efficiency by 3%. Although the system self-corrected, simulations confirmed that the same micro delay under different tank volumes can trigger a cascading imbalance between the methane and oxygen pressures, producing combustion instability strong enough to destroy injectors. The intellectual satisfaction of this analysis is the reduction of chaos to order, demonstrating the quiet inevitability of physical law. The verdict on the mission was not delivered by human judgment, but by by the plasma itself, with the laws of thermodynamics rewriting the engineering language in real time. The system's survival was an inversion. The overperformance of the structure compensated for the underperformance and loss of integrity in the heat shield. In the complex realm of motion, heat, and structural vibration, there are no absolute models, only provisional agreements with physics that will only last until reality updates the terms of engagement. Despite the survival, a critical uncertainty remains embedded in the physical fabric of the vehicle itself, a key determinant of the future vector of reusability. The stainless steel structure showed microscopic grain growth in the areas that endured the highest thermal load near the exposed gaps. Electron microscopy measured changes equivalent to a 5% to 7% loss in local yield strength. The vehicle survived this one wound, but each future flight reusing that hull will begin with a measurably reduced margin. The question of cumulative micro-damage and how many cycles the alloy can endure before cumulative damage demands replacement remains entirely unresolved. The most structurally threatening event occurred during the deorbit burn at T plus 154 minutes, when a harmonic oscillation with an amplitude of 0.17 G suddenly appeared. This vibration was precisely at the natural frequency predicted for the main methane tank bulkhead, plunging the ship into a critical resonance envelope. As Starship descended, aerodynamic buffeting fed additional energy into the oscillation, causing the bulkhead to flex 1.3 millimeters beyond nominal. The structural failure threshold was 1.5 millimeters, where weld seams near the feed lines could have cracked, meaning the entire system survived this inversion by a margin of only 0.2 millimeter. The control system compounded the thermal asymmetry with a cognitive error during the hottest phase of re-entry. The onboard software, which uses hundreds of sensor inputs to predict attitude drift, misread the heat flux distribution caused by the missing tiles. It incorrectly predicted lower drag on the damaged side, issuing commands to the flaps that resulted in a compensatory oversteer. This overcorrection caused a brief 1.2 oscillation in the angle of attack, which instantly changed local heating rates by 8% to 10%. The assumption of isolated damage was annihilated by the physics of heat migration, demonstrating that damage is inherently communicative. Instead of remaining localized, the damage area advanced across the belly of the vehicle. High-speed footage confirmed that light flares were traveling diagonally across the tile seams, indicating that plasma was cutting into the adhesive joints. This thermal advancement, measured at about 30 cm every 10 seconds, covered 2.5 meters over a minute and a half, demonstrating that heat was moving laterally through aerodynamic coupling. The critical near-miss tension was quantified 43 seconds after shock layers detached from the hull. The roll control system saturated, initiating a 2.5 attitude drift that exposed the starboard side to direct concentrated heating, causing a temperature surge of 80 C. Structural buckling would have started along weld seam A47 if the drift had continued for 6 more seconds. The system autonomously corrected in 4 seconds. That 2-second difference was the precise, quantifiable gap between controlled descent and a collapsed hull. The moral precision of the outcome is that the flight was not a celebration of human triumph, but a fundamental exercise in engineering calibration. The data shows that out of 18,000 heat shield tiles, 270 were intentionally altered, and 39 suffered additional erosion, none of which compromised flight stability. This result redefines the threshold of reusability. It proved that reusability does not require perfection, only predictability. By designing for imperfection, engineers expanded the safe zone, transforming the approach from fragile precision to robust tolerance. results. The lesson of procedural change immediately translated into the future vector of the design program. Records show that the subsequent Block 3 designs were modified to include flexible gaskets between tile rows, a measure intended to physically prevent the observed lateral plasma migration. Additionally, embedded pressure sensors were included behind select tiles, a new feature designed to detect plasma infiltration early in the re-entry sequence. This means the engineering discipline of reusability must now extend beyond surviving the heat to actively diagnosing stress before it compounds or cascades. The ultimate structural resilience was traced back to a seemingly inefficient design choice. Combined loads measured during the critical phase, peak dynamic pressure at 8.3 kPa, heat load at 1.8 mBm2, and tank pressure at 7.6 bar, should have technically exceeded the yield limit in at least one panel. However, the Block 2 hull used thicker gauge steel, 0.7 mm thicker than the previous Block 1 design. That added mass was a penalty during ascent performance, but the structural overdesign it provided was the physical mechanism that saved the vehicle during descent. The human process proved that rapid iteration is an effective tool for collecting data, but it can hide structural complexity under the pressure of speed. The lesson is that rapid testing reveals failure quickly, but it does not remove the need for slow, methodical analysis. The black box recorded thousands of variables during the flight, but the true meaning of those recordings only unfolded much later in the silence of the post-mission review. The system did not cheat the laws of heat and motion, it obeyed them with a new precision, utilizing the steel's ductility to allow minor warping instead of catastrophic fracture. The successful descent began its transition to final stability at 39 kilometers altitude, where the craft initiated its belly flop mode to maximize drag. The flow field finally stabilized, and the plasma surrounding the hull cooled from brilliant white to a manageable orange glow. After splashdown, telemetry streamed through low-gain antennas, confirming the metal lived and the insulation burned, the structural integrity holding firm, while the model that predicted its failure was proven wrong. The deepest systemic revelation came from the unmodeled coupling that had almost cracked the hull invisibly. NASA's reconstruction quantified the discovery. Pressure oscillation at 5 Hz in a high-pressure composite overwrapped pressure vessel, COPV, had achieved near-perfect alignment with a thermal vibration frequency of 4.97 Hz in the aft skirt. This resonance margin of 0.03 Hz created micro-impulses that transferred energy between the tank and the structure, invisible to the primary sensors. Records showed that if the resonance had persisted 5 seconds longer, the localized stress would have exceeded the yield point by 1.2%, initiating a minor fracture that would have compounded across future flights. The profound moral of aerospace engineering is that success is never safety. It is only a pause between the ultimate judgment of physical laws. The system meant to defy the gravity of this world and reach others continues to teach humanity how truth behaves under the load of thermodynamics. The ultimate reward is not courage, but meticulous calculation, proving that when the numbers align, even intentionally damaged steel can glide through plasma and return whole. The narrative concludes not with a victory banner, but with coordinates for the next test window. Unresolved questions remain a silent mandate for the future vector of the program. Can the vehicle maintain full reusability after repeated exposure to asymmetric heating? Will the cumulative microdamage compound in the weld seams across multiple flights? Can future autonomous control systems predict the nonlinear coupling between geometry and flow before telemetry confirms the error? The system has endured, but the margin for error is shrinking, and the silence between flights remains the sound of engineers recalculating the necessary humility before the indifferent yet precise authority of natural law.